CS626, and we started part-of-speech tagging. We will continue with this discussion now. Now, what we have seen in the last week is that there are these foundational concepts like Turing test and Chinese room experiment, which ask questions on intelligent behavior from machines, and also can the machines which display intelligent behavior, can they really be called conscious or not? And then we understood that NLP is a combination of linguistics and probability, which is language science and data science. And we emphasized the main functioning of large language models. That function is to predict. They predict the next language object or properties of input language objects. So we took the example of what is the capital of India. Delhi is predicted as the next language object. And the movie was very good. The sentiment is predicted as positive again as a language element, namely positive. We have also made useful observations with respect to computing by humans, intelligent behavior by humans, how efficient they are in terms of the size they occupy, the energy they consume, the carbon footprint they leave in terms of polluting the environment. And we also discussed well-known large language models, medium-sized language models, and small language models. And a very important notion of NLP stack, whereby we go from morphology of words all the way up to pragmatics and discourse analysis through shallow parsing, semantics, and so on. So this is what was our preoccupation last week. Now, I have also discussed last week the plan for assignments, the three assignments based on part-of-speech tagging, named entity recognition, and transliteration. Okay, they involve three important machine learning techniques: hidden Markov models and conditional based POS tagging. So HMM and CRF, both of them belong to one kind of ML technique, that is graphical models. Then support vector machine and logistic regression machines, which are binary classifiers. They are for named entity identification. And finally, alignment algorithms, which are based on expectation maximization. So statistical transliteration from Indian language to English. EM is also a very machine learning technique. And I have also specified that for all your assignments, you must compare performance with chatgpt, which will be quantitative figures, accuracy figures, and precision values, recall values, and so on. Now, the project plan also was discussed, and I said that the project should be based on one paper as the core paper, and there can be allied papers. Also, the project should be ambitious. You should have a fairly lofty aim, which is based on the core concepts of a single paper, but you have good value addition to the contributions made in that paper. Now, NLP layers is what we would be constantly referring to through the course, starting from morphology, which is analysis of words, and going up to discourse and co-reference, which is analysis of large pieces of text. And the passage is through shallow parsing, semantics. Shallow parsing again involves part-of-speech tagging, chunking, parsing, these as sub-activities. So let's dig deeper into the task of part-of-speech tagging. We describe part-of-speech tagging as the task of assigning grammatical roles to words as they appear in sentences according to their use. So the parts of speech which are well known and which you have studied in schools and colleges for your language lessons are 8 in number: noun, adjective, pronoun, verb, adverb, preposition, conjunction, and interjection. We also saw last week the part of speech tag hierarchy, namely two broad divisions of parts of speech: content word and function word. Content words are very important because they capture two important conceptual entities, namely things and actions, that is nouns and verbs. Now, nouns and verbs get qualified by adjectives and adverbs. They also fall under the category of content word. Function words are adposition, conjunction, and exclamation. Under adposition, we have preposition, postposition. So Indian languages use postposition. French, English, they use prepositions. So the example would be the word with, for example, which comes before the noun typically, except for some corner cases of English, where you can have a split prepositional phrase. Who do you want to go with? You do have such kind of construct. Who do you want to go with? So here the actual canonical sentence is with whom do you want to go? Instead of that, with has traveled to the end of the sentence. And we have the split preposition case. The word who and with are separated from each other by intervening text. So this phenomenon, interestingly, you do not see in languages which have postposition. So chammach se with spoon are always together. Okay. So function words and content words, and if you want to know their practical utility, information retrieval has to be very, very sensitive to how they deal with content words and function words. You will notice that in information retrieval, we give queries to a search engine, and queries in their shortest form almost always consist of only nouns. Okay. So for example, Qutub Minar, Delhi. Qutub Minar, Delhi. So where Qutub Minar is a named entity and Delhi is also a name. All these are nouns. Verbs do appear, but more rarely than nouns. So it is immediately clear that for search engine performance, which means retrieving the information, the relevant information at the top of the list of URLs which are retrieved, the nouns have to be handled very well. So Qutub Minar Delhi should bring at the top of the list of retrieved URLs the URL which refers to Qutub Minar, and Taj Mahal should not appear at the top of the list. So this is called relevance calculation, and the most relevant page should be uppermost. So this relevance is a function of the nouns in the query. So nouns have to be handled very, very well. There was a time when function words used to be removed from the query. So in, with, at, those prepositions or articles like the and the a and they used to be removed. But this stopword removal, this is called stopword removal. This does not take place these days. There are other ways of dealing with function words where the function words aid the relevance calculation process. They are present in almost all queries. The word the, for example, is likely to appear in many queries and in almost all the pages which are retrieved. And therefore, the does not have any discriminating role because they appear in all pages. On the other hand, a page which contains Qutub Minar and is placed higher than a page containing Taj Mahal has a discriminating power. So even though this is a basic grammatical concept taught in schools and colleges, they have immense practical utility in the form of search engines. Now, understanding two methods of classification, syntactic, semantic, adjective. For example, adjectives have syntactic classification, semantic classification, and so on. This we touched upon in last week. Now, in terms of the problem statement of part-of-speech tagging, input is a sequence of words, and output is a sequence of levels of these words. Now, sequence of levels of these words are position wise. So at every position in the sentence, first position, second position, so on, we have words which are observations. Okay, and these observations have to be assigned part-of-speech tags. So part-of-speech tags are looked upon as hidden information which get uncovered by the process of part-of-speech tagging. So we have a sequence labeling problem here, sequence to sequence mapping also you can call it, where a sequence of words is mapped to a sequence of part-of-speech tags corresponding to every position of the word. And this mapping is looked upon as a uncovering of hidden state, where the observations are sequence of words and sequence of part-of-speech tags are a sequence of hidden states. We look upon part-of-speech tags as states. Okay, so that's a very useful way, even though strange way of looking at the problem. How can part-of-speech tags be hidden states? What do you mean by these part-of-speech tags as states? They are looked upon as state facilitate use of a very powerful machine learning technique called hidden Markov model, which we will very soon take up for detailed discussion. Now, the problem of part-of-speech tagging would have been extremely simple. Okay, it would have amounted to just a table lookup where words and their corresponding part-of-speech tags are recorded. So they are recorded anyway, even now in the dictionaries or lexicon. But the challenge is that the words can have multiple parts of speech. You look at this example here, which is the case of the word close. Close can be adverb, adjective, verb, noun, all the four content word categories, which is interesting. So running close to the competitor, here close is an adverb. Close escape, where escape is a noun, close is a qualifier, and therefore close here is adjective. Close the door, it is an action, therefore close is a verb. Towards the close of the play, this is a case of close being noun. Interestingly, escape could be also a verb or noun. Now, close escape, and if escape has ambiguity of noun and verb, it poses a challenge for determining the part of speech of close. So if close, if escape is a verb, then close should be an adverb, because if this is qualifying a verb, it is an adverb. And if escape is a noun, then close should be an adjective because it is qualifying a noun. So you can see that there is a mutual dependency of part of speech tags between two adjacent words. The part of speech of close depends on the part of speech of escape, and part of speech of escape depends on the part of speech of close. So there is a circularity, which is why the disambiguation is challenging, and we cannot simply make use of a table lookup for the simple reason that the words, first of all, do not have a single part of speech offense, and the choosing of the correct part of speech is a matter of classification, solving a classification problem. So now we will go back to the NLP stack. The NLP stack, as you recall, is this. We start with morphology and go up to discourse, coreference, pragmatics, passing through part-of-speech tagging, chunking, parsing, and semantics. So look at the positioning of part-of-speech tagging. Part-of-speech tagging is immediately above morphology, so it is at the it is one of the lowest levels. In fact, the second lowest level in the NLP stack, which means it is a very basic activity which feeds into the layers of chunking, parsing, semantics, discourse, coreference, and so on. So part-of-speech tagging being correct is crucial for the correct functioning of the upper layers of NLP stack and also downstream applications. Now, we'll take this interesting sentence and see how the NLP stack actually handles the processing of this sentence at different layers. So the sentence is to bank, I bank on the bank on the river bank. To bank, I bank on the bank on the river bank. So here to bank means to carry out banking transactions. And I bank, I depend on the bank, some bank on the river bank, which is situated on the river bank. So clearly, the first two banks are verb, and the second pair of banks are nouns. So I bank on the river bank. I do transactions in the bank, which appears as the third bank entity in the list of 4 banks in this sentence. So this is the meaning of the sentence. So now let's see how the sentence passes through different layers of NLP stack, and part-of-speech tagging happens for the sentence. So to bank, to is a preposition, and indeed, IN is the preposition level, which comes from the pen tree bank, which is a very standard tag set for English language. So to gets the tag IN. This is correct. Then bank, this is a verb, and VB is the level for verb in base form, again correct. Then there is a comma, this is given the level punct, P-U-N-C-T, meaning punctuation, correct. I, PRP, pronoun, fine, bank, VBP, verb in non-third person singular present tense. So VBP is bank, and I bank, this is correct part-of-speech tag for the bank that appears in the sentence. On is a preposition, and therefore the tag is correct, IN. The is a determiner, so DT is correct, determiner. This bank after the is NN, which is noun, again correct. On is a preposition, IN, correct. The is determiner, on the bank, on the river bank. River is NN, noun, and then a bank, which is singular noun. So all these parts of speech tags are correct. This is the output from chatgpt, and it's clear that it is able to disambiguate all the banks properly. Okay, so the first bank is verb, second bank is also verb, third bank is noun, fourth bank is noun. All these are correctly detected by chatgpt. Now, we will, of course, spend a lot of time in higher layers of NLP, but let me show the output of chatgpt for the sentence which we are considering now. I asked chatgpt to produce what is called the constituency parse tree for the sentence. To bank, I bank on the river bank. So this is a sentence. This whole thing is a sentence. So S is the symbol signifying that under S, we have a big tree indicating the parsing structure or the syntactic structure of the sentence under consideration. So S has starts with the preposition phrase to bank, which is fine. And then we have a comma, and then we have another S. So this S within S means that a sentence can contain another sentence. This is known as embedding. So there can be embedded sentences within sentences. I bank on the bank on the river bank. This whole thing is a full sentence. And let's look at the last line in the output. It says NP DT the NN river NN bank. So this means that the river bank is a noun phrase. NP means a noun phrase. So DT NN NN is the part of speech tag sequence. It is helping the syntactic analyzer or parser to detect the phrase correctly. So this is the constituency parse. Then I asked ChatGPT to produce the dependency parse. And in case of dependency parsing, the key challenge is to obtain the main verb of the sentence. That is the first step. And once we identify the main verb, we link all other entities in the sentence with the main verb. So here we see that ChatGPT is able to correctly identify a bank, okay, and that is indicated by an arc from a specialized node called root to the word bank, and the label for that arc is RWT, small rWT, which is the label. So this indicates that the bank, which is the second bank in the sentence, is the main verb. Okay, this is the indication that this is the main verb. So clearly, the machine is solving a classification problem continuously. Okay, so first of all, it has to identify which amongst all the words in the sentence is the main verb. That's a significant classification problem. So you can imagine a classifier running over the sentence word by word, and at each word it asks, is it the main verb or not? So it's a binary classification problem. To, no. Bank, no. Punctuation, no. I, no. Bank, yes. So how does it do that? That's a very, very non-trivial problem. Initially, there were rule-based attempts to identify the main verb, but the main verb appears in so many different syntactic environments with so many nuances that we had to resort to data. Now, this, by the way, is the message of modern NLP, that to identify any kind of regularity within language data, which is the concern of NLP, we have to make use of data and machine learning techniques. This is the bridge between machine learning and natural language processing. So much so that NLP is sometimes called applied machine learning. Okay? And NLP provides lots of interesting problems for machine learning techniques to work on. On the other hand, NLP is also dependent on machine learning for supply of techniques. So it is a win-win situation for both fields. ML supplies techniques and NLP supplies problems to work on. Then from dependency parsing, this is another slide describing, giving more details of the dependency parsing, but we'll discuss dependency parsing in much more detail later. Then I ascend the NLP stack further and go to the layer of semantic roles. So in case of semantic roles, the main tasks are two: words and disambiguation. Part of speech tag disambiguation identifies the correct grammatical level. Words and disambiguation identifies the correct meaning of the word as it appears in the sentence. So from the sentence that we have been dealing with, to bank, I bank on the bank on the river bank, there are 4 appearances of the word bank, each with a different meaning. Okay, so the first bank is a verb, indicates transaction, financial transaction. The second bank is the main verb, which means to depend. The third bank is the organization bank, and river bank is the side of the river. So each of the word appears in a different sense. So semantic roles identify the correct senses of the words, which is needed to identify the roles of various noun phrases and verb phrases in the sentence. So clearly, since phrases are involved, semantic roles get identified based on the syntactic information. So to bank is a preposition phrase and it indicates a purpose. So the semantic role of this phrase is purpose. Then I bank is the core of the sentence, which is a noun and a verb combination. The verb happens to be the main verb. Here I is the agent. So R0 indicates the first argument of the word bank. What is an argument? Argument is the noun phrase or noun that is required to meet the sentence formation demand of the verb. Verbs themselves, by themselves, they cannot form sentences. They need nouns to supply their sentence forming demand. So I is the agent and verb B, bank, is the verb. On the bank, on the river bank, here there is a location argument, which is on the river bank. Okay. And bank on the bank on the river bank. Here we have the semantic role, which is little more subtle. What does banking on the bank on a bank mean? What semantic role should be assigned? We see ChatGPT has not done a good job here. On the bank, on the river bank, what is the semantic role of this whole preposition phrase, which is a large one, with respect to the main verb, which is the I bank. So I bank on the river bank, the semantic role is close to a kind of purpose. However, on the river bank is correctly identified as location. Okay. So, so of course, ChatGPT would have its limitations for extremely complex tasks. We know it often gives wrong results. The most interesting case is that of pragmatics. Now we know that ChatGPT, which is a form of generative AI or NLP, is extremely good in fluent output. Now the fluent output may have mistakes, it can hallucinate, which makes difficulties for semantics and pragmatics. So pragmatics is now the layer working on the sentence to bank, I bank on the river bank. And it is fed with additional information from lower layers, in particular from the layer of semantics. What does semantics supply to pragmatics? It supplies the disambiguated words, the correct meanings of the words, and the semantic roles of the phrases with respect to the main verb. Okay, then we begin to apply pragmatic processing. Now, pragmatics is dependent on a few foundational activities. The first is speech act. So I'll not explain I'll not give the definition of speech act because that is for a later discussion. Speech act is expressed this way here by ChatGPT. The speaker is likely making an assertion about their reliance on a specific place or institution with a playful twist. So the fact that there is a notion of reliance, which is expressed in the sentence, is correctly detected. And the fact that it is a playful twist is also detected. By the way, the playfulness involved in this situation is not expressed in the words of the sentence. The sentence does not say that I am playful, right? The fact that it's playful is an extra sentential information, and this is characteristic of pragmatics. The notion of pragmatics came into linguistics and NLP because of the fact that semantics and syntax and lexicon do not capture everything that is inherent in the sentence or the way it is used. So we see that the playful twist is not there in any part of the sentence, but it is inferred from our word knowledge or knowledge of language. Similarly, inference. It is another element of pragmatic processing. The listener is expected to recognize the word play and understand that the same word bank has multiple meanings in the context. Yes. The speaker's choice to use all these meanings in one sentence suggests an intention to amuse or engage in linguistic creativity. So the fact that it's a linguistically very, very creative example is, of course, beyond doubt, because the word bank has been used 4 times, all in different senses, and and 2 of them being verb, 2 of them being noun. So the speaker's intention is to impress the listener with the linguistic creativity of the sentence. So this is also a pragmatic consideration. Linguistic creativity is not mentioned explicitly in the sentence. Then implicature, the sentence implies a clever use of language. The speaker might be highlighting their wit or drawing attention to the complexities of the English language, which is also true. And then contextual appropriateness, the sentence would be appropriate in a context. So this is a very, very important feature of pragmatics. Okay, so this is sometimes expressed in Hindi very well by saying, कहा क्या बोलना है समझना चाहिए. Okay, how and what we say in which situation is a matter to be very keenly attended to. So contextual appropriateness, this sentence would not be appropriate in a plain formal discourse. Okay, suppose I'm discussing a project with my team members. This kind of sentence will not be appropriate at all. People would be amused or think, or it will lose the or reduce the seriousness of the situation. However, it will be very highly appreciated in a causal conversation, in a language game, or a literary context. Very much so. So this is the notion of pragmatics, and ChatGPT very well describes the whole pragmatics involved in the sentence that we gave to it. To bank, I bank on the river bank. Now, if the question is how is it doing it? Oh, well, it is doing it from its training, which is pre-training actually. Lots of parameter values are fixed by lots and lots of corpora, and then fine-tuning with pragmatic data. So for example, this kind of sentences are given, and all these description of implicature, speech art, contextual appropriateness are also documented along with the input. And the whole thing is passed as fine-tuning data on the large language model. And then next time the large language model is able to deal with new sentences with proper, what is called prompting. You have to instruct it properly. You have to say that, give me the pragmatic elements of the sentence. Now, coming to part of speech tagging, we have understood that we need data for training a model for doing part of speech tagging. We are still waiting for an answer to the question, why not a rule-based part of speech tagging system? Why at all go for machine learning and data? This is a question which we need to ask always for any kind of NLP problem which is attempted to be solved with machine learning. So the first question is this problem appropriate for being subjected to a machine learning technique, which will require, of course, data in raw form, in annotated form, and so on. And equally important, but coming second in the sequence is the question of which machine learning technique I should use. Should I use a neural network or support vector machine or some kind of graphical model? Which one should I use? Of course, in this particular lecture, we'll solve the problem making use of hidden Markov model. Now, the data appears in this form. The raw sentence is first taken. Who is the Prime Minister of India, which has 1, 2, 3, 4, 5, 6, 7 words, but 8 tokens. There is a punctuation mark also. And the data is annotated with these part of speech labels. Who is WP, which is who pronoun. Is VZ, auxiliary verb. The is deity, determiner. Prime is JJ, adjective. You can immediately spot the ambiguity. Prime can be also a noun in the prime of his life, for example, in the prime of his career. So prime, there would be noun. Minister can be a verb also, right? Minister is a noun, but it can be a verb too. Of is a preposition. India is a proper noun. And then punctuation, question mark is a punctuation. So this is the level. These are the levels which are given to the words. And that read is the sentence to be used as a fodder for training the machine learning model. These part-of-speech tags are as per the Penn Tree Bank tag set. So we have got the raw sentence. We have attached part-of-speech levels to the sentences, and they are now ready for training a machine learning model. So we started discussing machine learning based part-of-speech tagging through this framework, all important framework based on argmax computation. We said that the raw input sentence will be subjected to a computation by a noisy channel, and out comes the sequence of tags. So W is the input word sequence. T, capital T, is the output tag sequence. Now, many possibilities exist for the tag sequence, just because the words have multiple tags. And we have already discussed this point that, let's say in the worst case, every word in an n word sentence has k part-of-speech tags. Then we can see that there are k to the power n possibilities, and we have to choose one amongst them. Which one shall we choose? We need a metric or a score for each of these part-of-speech tags sequence, and we'll have to choose that one whose score is highest. The scoring is done by probability. Okay, that is what is captured by this formula here. T star is equal to argmax probability of T given W. That means you give that tag sequence as the answer whose probability is the maximum given the word sequence. So this is very well expressed by the argmax function. Argmax says that I'm getting the highest probability T given W, and but I'm returning the T. Okay, not the probability value, but T. So this is the argmax expression. Now, this I remarked came from the noisy channel metaphor, which came from automatic speech recognition. So the researcher who is responsible from this framework and who can be called as the father of data-driven natural language processing or machine learning assisted natural language processing is Dr. Jelinek from AT&T Bell Labs, who is no more, but has made immense contribution to speech recognition and similarly to NLP also. Now, this probability expression, T star equal to argmax P T given W, is now subjected to Bayes' theorem, and we introduce a prior probability and posterior probability in the formulation. Now, one key question that arises in application of this kind of probabilistic score computation and application of Bayes' theorem is, should we work with the right-hand side or the left-hand side of the expression? Should we work with B given A, or should we work with PB and PA given B? Of course, the denominator we understood can be dropped because it is independent of B. It doesn't vary with B, and therefore it can be dropped from the computation, because after all, ultimately we are interested in ranking of different values of B and choose that value which has the highest probability. So PA can be dropped. So should we work with the parameter PB given A, or we work with the pair of parameters PB and PA given B? Okay, so you can see that the conditioned random variable and the conditioning random variable are turned upside down from the left-hand side to the right-hand side. So to understand this question, let us look at a few two non-LNP problems. So let us consider the case of cancer detection and visa granting, both of which are actually classification problem. The first problem asks, the cancer detection problem asks, does a patient have cancer? The patient's lab reports, body parameters, okay, all these are brought in, and the doctor also examines the student physically. And from these, a set of values for different parameters for the patient are obtained. Based on this, we have to decide if the patient has cancer or not. Since we have taken the probabilistic path, we are saying that the patient has cancer if probability of cancer is greater than probability of not cancer. A probability of not cancer is 1 minus probability of cancer, which leads us to the observation that the patient has cancer if the probability of cancer is more than 0.5 as per the observation of the patient. Similarly, visa application. An application for granting visa is submitted. Now, from the application, we obtain various features of the applicant and then compute the probability of grant visa, okay, given the application parameters. And if the probability of grant visa is greater than 0.5, we grant the visa after. Now, the question is, if in case of cancer, should we deal with probability of cancer given the patient parameters, which is one way of approaching the problem? Or should we work with the two probability values, the probability of cancer and the likelihood probability, which is the probability of the cancer of the patient having these characteristics, given that he or she has cancer. So these are the probability values we have to work with. And the probability values, of course, have to be computed from data. We cannot manufacture, okay, or imagine probability values. The probability values are completely dependent on the data that is available to us. Now let us examine the probabilities involved in the case of cancer detection. We have the posterior probability of cancer given patient parameters. The patient parameters are HbC, hemoglobin count, weight, family history, and so on. This can be as long as possible, can be as complex as possible. But the essential formulation is this. We have to compute a posterior probability of cancer given patient parameters. If we apply Bayes' theorem and work with the right-hand side, then we are actually entering computation using generative model. Then we have to deal with two parameters: prior probability of cancer, and the likelihood probability, that is probability of patient parameters given the patient has cancer. Now here come a deeper look at how this probability is computed. The probability of cancer will have to be computed from a sample of the whole population. Okay, so the population that we are interested in, maybe we are interested in the population, in a population called let's say people who smoke cigarette. Okay, so we take this sample of people who smoke cigarette and see how many of them eventually got cancer. So prior probability will be obtained from this data. So how many of them got cancer divided by what is the size of the population. By the way, this ratio will have to be now asserted for the whole population. And we know that if the sample size is not large enough, we cannot claim this, that this is the prior probability of a person, an arbitrary person, a random person having cancer. But surely this parameter, probability of cancer, is obtained from the sample of factory cigarette smokers. The likelihood value is again also computed from data. We'll have to take the a sample from the population of cancer patients. And out of those cancer patients, we find out how many of them have a sequence of patient parameters. Here again, there is a complexity. The patient parameters is a set of parameters, and we have to maybe make use of naive-Bayes assumption and say that the parameters are independent of one another. So I can take the product of these probability values. Probability of hemoglobin count being low, given that the person has cancer. This has to be estimated from the data. How many cancer patients had hemoglobin level below a particular threshold? Okay, so this is the way we are computing these probability values, as you can see. Now, if we had to work with directly with posterior probability, then we are interested in this probability value, probability of cancer given patient parameters. Now, this is not very obvious. It's not very obvious how to get this kind of values. So here we'll have to consider a population which has both cancer and non-cancer patients, non-cancer and non-cancer persons, and obtain their parameter values and see how many of them actually had cancer. So this particular sample is not very reliable, not very well articulated or well expressed, not very well determined also. On the other hand, if all the parameters on the right-hand side are fine, P-cancer you can obtain from a sample of the whole population that we are interested in. So let's say the people who smoke cigarette, okay? And then the probability of patient parameters given the person has cancer. This is obtained from a sample of people who had cancer. Okay, so that is a very definite sample from a population. The population is also well defined. It is the population of cancer patients, and how many of them have low HBC count. Low means below a particular threshold. So this is also quite easy to determine. So in case of cancer detection, working with the right-hand side parameters, namely prior probability and likelihood, seems to be a good idea. Okay. Now let's consider the other classification problem, which is whether to grant the visa or not. Okay. So in this case, again, we have to compute the probability of grant visa given a candidate features. So here, the way it will be, the probability will be calculated is that we take various candidates and obtain their features like income, education, travel history, etc., and see how many of them are granted visa and how many of them were not. Okay, so that these statistics will help us obtain the decision with respect to visa. If we work with the right-hand side, then we'll have to find out how many, what is the proportion of people who were granted visa. Okay, so that will be coming from the population of applications. And then if for those patients who were granted visa, what were the features? Okay, so this also seems like an elegant framework. So in this case, it seems that posterior working with the posterior probability, vis-a-vis working with prior probability and likelihood, both have equal merits and demerits. But in case of cancer patient, the indication was strongly in favor of working with the right-hand side of the formulation, which is prior probability and likelihood probability. So this is what is involved. Okay, I hope it has become clear to you through this discussion, how data is used to compute probability and how these probabilities are used to make a decision. At the heart of all these things is this point about probability of a decision given the data should be more than 0.5. Last time we were discussing this sentence, the part of speech of the sequence of words, the sun is shining. So we were interested in this probability, the probability of DT, NN, VVZ, VVG, which is a determiner, noun, auxiliary verb, and gerundial verb form. So the dt, sun nn is VBZ and shining is VBG. So we have to get the probability of this sequence given the word sequence the sun is shining. Now in this case, we have to compute the probability, joint probability of dt, nn, vbz, vbg along with the sentence divided by the probability of the sentence the sun is shining. So this can be computed from the data by here is a bit of a mistake here. The numerator should be the number of times dt, nn, vbz and vbg appears with the sentence the sun is shining divided by how many times the sentence the sun is shining appears. So we have discussed in the last class that this kind of computation is infeasible. You cannot go ahead with this kind of computation. The reason being that the sentence which is obtained can be a completely new sentence. Nothing like this has been seen in the corpus. Okay, the sun is shining. That's a simple sentence. It will appear in the training corpus, but there can be complicated sentences. Maybe a very, very long sentence with 150 words. That is very unlikely to appear in the sentence, in the training data. Okay, so now here, let me make a small reference to the reason why LLMs are so powerful. The LLMs like GPT-4, GPT-4o, Gemma, Gemini, etc., they have at their disposal a huge amount of data. And we have also remarked last time that the length of the conditioning part also can be very, very large. Some 400 words can be in the conditioning part. These are extremely large search space. Okay. And it is because the ChatGPT or GPT-4, GPT-4o, Gemma, because they can accommodate such a long context that with huge amount of data, it is almost always the case that the training data, the test sentence was seen before. And at the time, the correct decision was made, and now it's a matter of just retrieving the decision and outputting it. Okay. However, when we are dealing with small amount of data, this will not be the case, and we'll have to think of each sentence as processing. So the probability of the number of times this sequence and the word sequence appears together, that data we need, that number we need, and we also need how many times the sentence appears in the training corpus. And the sentence may not appear. So what do? We have to make use of dealing with the smaller parts of the sentence. Okay, the sentence itself may not have any evidence in the training data, but its parts may have evidence. So that led us to the argmax-based formulation. T star, the best possible tag sequence, is argmax of probability of T given W, which can be converted by application of Bayes theorem to probability of T into probability of W given T. So we saw in the last class that in probability of T, which is the probability of the whole tag sequence, we can apply the chain rule and obtain the probability product of probabilities, probability of T0 into probability of T1 given T0, probability of T2 given T1 T0, probability of T3 given T2 T1 T0. This is the way it is. And as we do so, we are applying the chain. There is no approximation going from the first step to the second step. But this is just transferring the complexity to another location without any simplification whatsoever. So now we apply Markov independence assumption and say that every tag depends only on the previous tag. Thereby, we have a product of what is called bigram probabilities. Probability of T0, which is always 1. Probability of T1 given T0, T2 given T1, and so on. These are called transition probabilities. And these transition probabilities are like state-to-state transition. So T1 is a state, T2 is another state. So we move by state to state transition on the tag sequence. So the product of these bigram probabilities is the product of transition probabilities. Now we come to the likelihood part, which is probability of W given T. Here also we can make use of the chain rule and see that probability of capital W given capital T is nothing but probability of W0 given the whole tag sequence into probability of W1 given W0 and the tag sequence, probability of W2 given W1, W0 and the tag sequence. Now, this is also a very cumbersome expression, impossible to deal with. So we now apply another Markov independence assumption and say that the probability of the word appearing in a position is totally dependent on the tag at that position. So the observation depends only on the state at that position, and therefore we can convert the probability expression into product of observation probabilities. So probability of W0 given T0 into probability of W1 given T1, probability of Wn plus 1 given Tn plus 1. So then we have a product of observation probabilities and the product of transition probabilities. So transition product of observation probability product of transition probability and the observation probability can give rise to a situation where the transition probability and observation probability can be multiplied. Okay, that we will see as we go ahead and enter discussions in hidden Markov model. Okay, so here is a situation where the POS tagging depends on the transition probabilities and observation probabilities. Okay, it's a sequence leveling task which is dependent on transition and observation probabilities. Is there a machine which gives me transition probabilities and observation probabilities? Indeed, there is one. That machine is called hidden Markov model. Okay, so we see that from bigram probability and observation probability, we can have a machine where the machine has the word sequence. Okay, the word sequence is recorded there as observations. So people jump high is the sequence. Now people jump high. People can be noun and verb. Jump can be verb and noun. High can be adjective or adverb. Okay, so these possibilities are recorded here. Now, when we have a word and on top of it, the possible tags are recorded, this is called a trellis diagram. Okay, this diagram is called a trellis diagram. And we start with the hat symbol, which is the beginner of the sentence. And we end with the dot symbol, which is the finisher of the sentence. Now, here we have given NV, VN, and AR as the trellis elements. The first element for the computation is hat, and it goes to dot, okay, passing through all these intermediate stages. Now, the whole task now becomes finding a path from hat to dot such that the path has the best score. The best score means the path probability should be the highest. Now, the path probability can be computed as the product of arc probabilities and the observation probability, okay, multiplied by the next one, next transition probability and the observation probability, and so on. So this becomes a conceptually very simple framework where we keep taking the product of transition probabilities and observation probabilities as we examine a particular path. Okay. Now, in the path, you see we have these observations whose probabilities also you have to take into account. So how is the part-to-speech tag finally given? So that process is known as inferencing or decoding. Let us illustrate this with an example. we have an input sentence here, which begins with the hat symbol. And then we have brown foxes jumped. The brown, we have brown foxes. Let me see the sentence. Brown foxes jumped over the fence. That is the sentence. So hat is given the tag hat. Brown actually should get the tag adjective, but has possibilities of both noun and verb. Foxes can be verb and noun, but here it is an S noun. Jumped is the main verb of the sentence, and it can be VBD or JJ if we do not have the context. Actually, it is VBD. Over is a preposition, that's why IN. The is the article DT, and fence is a noun. So we start with a root node where we have the hat symbol, and the next possible tags are given as children of this root node. Then for every tag which is placed as a child of the root node, we can have grandchildren. So from NN, from hat, I can go to NN or JJ. From NN, I go to NNS and VBS. No, okay. So foxes, for foxes, it can be NNS or VBS. And from NNS, again, I can have VBD, JJ. VBD, I can have NN, IN, JJ, RB, and so on. So this way, we will have a tree where we have first K children, then K square grandchildren, then K cube grandchildren, assuming that for every word, okay, we have all possible tags. If we do not want to be very particular about what tags to start with, because ultimately we are interested in the path probability. And also those tags which do not appear in the training data at all, their transition values will get 0. So they will not have any effect on the path probability. In fact, wherever they appear, this path will have 0 probability. But anyway, let us consider a situation which is simple to handle. So for every word, we'll assume that all words in the repository are possible. So we start with one word, then one node, and then we have K children, then K squared children, then K cube children, and so on. Finally, K to the power N children. Okay, and it's a huge tree if the sentence is very long and the number of also, let's say 40. Okay, a very large number of possibilities. Now we have to find out the best possible path. So the best possible path is found out by computing the probability of the path, which is pt.pw given t star. So p star into pnn given star, pn given nns, nn, p vbd given nns into probability of nn given vbd into probability dt given nn into probability nn given dt, probability of nn given full stop, and probability of full stop. So this finishes the part on the transition probability of the computation. The next part is observation probability. Probability of hat given hat, which is always 1. Probability of brown given NN. Probability of foxes given NNS, and so on. Now, given that the word is a noun, what is the probability it is brown? It will be very small. Okay, brown is one amongst many nouns in English language. So probability of brown given noun will be very small. Similarly, probability of foxes given NNS will be very small. So observation probabilities typically are very low. And therefore, we often work with not probability values, but with log of probability values. Now, log is a monotonic function, and therefore, if we rank the possibilities using log of probability, it doesn't disturb the ranking of the elements. So working with log is fine. Then we'll not face the problem of extremely low value for this probability values. Okay, so the loss of precision will not happen. Now, if there are questions like where do the tags come from? So this comes from what is called a tag set, and how to get the probability values. We get those probability values from the annotated corpus. And after modeling of the problem, that is, once you've decided what machine to use for part-of-speech tagging, we should give emphasis to the training data or the corpus, which will supply the transition and lexical probability values. So computing the probability values is a matter of computing ratios, which happens through the application of a principle called maximum likelihood estimate. Okay. Now, this is the so this is the finite state automaton which we have obtained given the sequence of words and the transition and lexical probability values. Now we enter the discussion on the technique which is underlying all this discussion, the hidden Markov model. Now, hidden Markov model is a technique, so it comes in the algorithm axis of this three-dimensional picture of NLP Trinity. I call this NLP Trinity because there are three axes of language, problem, and algorithm. So if you're creating a part-of-speech tagger for French using hidden Markov model, then we have located ourselves in a point, at a point in this whole three-dimensional space. So the hidden Markov model is always illustrated by this example, which is from Professor Rabinar's very well-known tutorial on hidden Markov model. This is most likely the second most cited paper in the area of AI machine learning. The highest citation going to the paper by Dempster Schaefer on expectation maximization. But this also has huge number of citations. And the example itself is quite good to illustrate the concept of transition and observation. Now, at this point of time, let me digress a bit for an interesting situation. I have been going to different universities. Once I went to Jerusalem University in Tel Aviv, and my host came to pick me up from the airport. So my first question was, or one of the first questions was, is not Professor Rabinar a faculty member in Jerusalem University? And my host, feigned a kind of irritation, asking, why is it the case that anybody who comes to Tel Aviv and goes to Jerusalem University asks about Professor Rabinar? So that is the kind of popularity of Professor Rabinar, and that is due to this tutorial that he wrote on hidden Markov model. A very, remarkable paper which has stood the test of time is referred to by generations of students and researchers. And this has made Professor Rabinar also a household name as far as machine learning is concerned. Now the problem setting is as follows. We have three urns, urn 1, 2, and 3, or containers, urns or containers, where the first urn has 30 red, 50 green, and 20 blue balls. The second urn has 10, 40, 50. Third urn has 60, 10, and 30. So everywhere the total number of balls is 100. So it so happens that the transition probability table has both row sum and column sum as 1. So column sum being 1 is a coincidence. Okay, one should not have a wrong notion that this should be the case. The column sum should be equal to 1. That should not be the case. Now we come to the table which is called the transition probability table. So the transition probability table says for every cell, for example, if you take the first row, U1 column and U1 row, U1, the column is the destination urn, row is the source urn. So the probability of going from U1 urn to U1 urn, that means remaining in U1, is 0.1. Probability of going to urn number 2 from urn number 1 is 0.4. probability of going to arm number 3 from arm number 1 is 0.5. How do we get these probability values? We have collected data, for example, by observing people picking up balls from the arm. Now, what is the actual task? I was describing all these probabilities without first describing the task. The task is the following. If we have made the observation of the colors of the ball, let's say we see a red ball, a green ball, then a blue ball, then a red ball, and then a green ball, and then the red ball. If we do it this way, then we have made this observation of RRGG, BRGR. The question being asked is, what is the most likely sequence of arms from which the balls came? The balls are picked up from each arm with replacement. So I pick up a ball from arm 1 and replace it there and note the color. So clearly, since this is with replacement, the observation probability table is easily constructed. So there are 30 balls out of 100 in the first arm. So probability of drawing a red ball given the arm is U1 is 0.3. Similarly, probability of G given U1 is 0.5, probability of B given U1 is 0.2. So this is how the observation probability table is created. So observation probability table comes from the way the arms have these different colored balls, and the transition probability table comes from the data of observing people, picking up balls and giving the sequence of colors that they got. So many such sequences are observed, and the transition from one arm to another is observed. They are recorded, and then by maximum likelihood estimate and the ratio of such counts, we obtained the probability values. So for example, the probability of the value of 0.4 under U1 row and U2 column, we got this value from the data of observing how many times people who chose a ball from arm number 1, then next time chose a ball from arm number 2 from that observation. So the total number of times we went from U1 to U2 and total number of times we were in U1, that ratio gives us the probability value. So transition probability, observation probability, these two tables are given to us. There is one more table which I have not shown here, that is called the initial probability table. The initial probability table gives the probability of starting from U1 or U2 or U3. Obviously, the initial probability values have to sum to 1. So these probability values, the transition probability values, observation probability values, and the initial probability values, all these 3 sets of values define a hidden Markov model. Okay, there can be infinite number of hidden Markov model. Hidden Markov model as a machine is 1. But there can be many instances of hidden Markov model where they differ from each other in terms of transition, observation, and initial probability values. Now, there is a nice depiction for this transition, observation, and initial probability value, or a nice depiction of the hidden Markov model, provided the transition probabilities are based on bigrams. Okay, so in that case, we can draw the diagram which is shown on the screen. We draw 3 circles corresponding to 3 arms, U1, U2, and U3. Then we draw arcs from U1 to U2, U1 to U3, then U2 to U1, U2 to U3, and so on, and then record the transition probability values on these arcs. Okay, so for example, we said that the probability of remaining in U1 from U1 is 0.1. So that's why there is a self loop for U1 state, and the value on it is 0.1. Then there are arrows emanating from the states, and the values on those arrows are the observation probabilities. So we know that there are 30 balls in U1 out of 100 which are red. Therefore, the probability of R is 0.3 on an arc which is emanating from U1. Now, working with machines which have outgoing arcs which do not go to any state and arcs which go from one state to another, working with such machines is cumbersome. Okay, what we can do is that we can absorb the probability observation probabilities also in transition probabilities. So from U1, we have three arcs. So I have shown only one arc. We have three arcs going into U1. And those three arcs are R and U1, G and U1, B and G1. So what is the probability of remaining in E1 while picking up a red ball or green ball or blue ball? So this probability can be easily computed because we are dealing with the product of observation and transition probabilities. So 0.1 into 0.3 is 0.03, 0.1 into 0.5 is 0.05, 0.1 and 0.2 is product is 0.02, and so on. So we have got only now state transition arcs and the corresponding probability values. Those probability values are nothing but the product of observation and transition probabilities. Okay, so we will discuss more on this machine of hidden Markov model and the way they're used in producing the part-of-speech levels. Whatever with the machine, we have already understood that we have to choose from amongst many possibilities. Now, when we choose from amongst many possibilities, we encounter an exponential search space. But exponential search space need not be the case. The reason is that we can make use of pre-computed probability values or pre-computed path values, especially the subpaths. So for example, if I have computed the probability values of probability of the whole path starting from hat going up to dot through the topmost path, then for computing the probability value of the second topmost path, we already have the probability values and the products for the first two arcs. Okay, so why should I compute that again? I should make use of this in my second path computation, third path computation, and so on. And this is nothing but dynamic programming in action. And an algorithm which makes use of dynamic programming to cut down the search is called Viterbi. Viterbi and hidden Markov model go together. Viterbi algorithm uncovers the state sequence extremely efficiently from the observation sequence. So we'll go into those details in the next week lectures. Thank you. Was it recorded properly or